So I'm going to work through a concrete example, and I'm going to use, well, so a concrete example of taking a kind of model from engineering and mapping it into a PVR plus model. That's what I'm going to do. And I'm using as my example the battery model that is described in both the ICAPS paper and the JER paper that exists on the policy learning technique we applied to battery management. But in there, the actual modelling is very much abbreviated, so I thought I'd just go through all the really gory details now to actually see how you go from an engineering model into a PVL plus representation that captures the key aspects of the behaviour that you're interested in. And I think I just want to make one point to connect with the discussion, the questions that Derek's been handling, which is to say that even if some of the modelling characteristics of PVL plus, like if you're trying to capture a bouncing ball or something like that, seem unnatural, and you think, well, the modeller wouldn't meant to put that in, and so on and so forth. That's true, but if you want a language that's capable of expressing and correctly capturing behaviour of a hybrid system, then it has to be able to account for those sorts of behaviours, as well as for behaviours that are less pathological in their nature. So I think that hopefully this concrete example will show something about how we go about using the language or to describe something practical. So this is about the essentials of basically lead-acid battery behaviour, although the battery model that we use is a little more general, but it's typically used to describe lead-acid batteries. And the problem that we looked at in the previous papers that I mentioned is when you've got two or more batteries being used to power a device, then efficient use of power can be achieved by planning. So the planning problem is to switch between the different batteries to supply the necessary load. And that switching gives the individual batteries time to recover, just according to the normal chemical processes of batteries. Okay, so what we have, so this is just to show you the basic behaviour we're interested in. So if you consume charge from a battery and then give it some time to recover, then basically the charge that's bound up in the chemical properties of the battery will move into becoming available so they can be exploited to service a load, and then you can access overall more charge from the battery. And if you've got multiple batteries, then you can kind of choreograph this consumption recovery behaviour to try to access as much as possible of the capacity of the battery. Okay, so what we really want to capture in our planning model for deciding how to switch between these batteries is the basic discharge and recovery processes of batteries. And the model that we take from the engineering domain is the kinetic battery model, which describes the behaviour of these batteries. It was proposed by Manuel McGowan back in the 90s. It describes these batteries in terms of there being two wells. One is the free charge or available charge well, which supplies electrons directly to the load, which is I, which is the load at some time t. While the other well, which characterises the charge that's bound up in the battery, only supplies electrons to the free charge well, and does it according to this charge flow, which is the conductance between the two wells. And the flow rate depends on the height difference between the two wells. Okay, so we have these two key parameters. One is delta, which is the height difference between the two wells, and one is gamma, which is the sum of the two amounts of charge, that's the total charge in the battery. Right, and C, little c, is the proportion of the capacity of the battery that's free in the initial state. So that's here. And then we have two other variables, y1 and y2, which are the amount of charge in the free well and the bound well. And actually we can see the charge in these two wells in terms of area, and then what we can say is that given that C is the amount of charge that's available in the, so the amount of the capacity that's available in the first well, then the height of the charge in that well is given by y1 over c, and the height of the charge in the other well is given by y2 over 1 minus c. Okay, so those are just some variables and their definitions that we obtained from the kinetic battery model. Okay, so then we have a mathematical model of the problem in which we have these two variables, the heights of the free and bound wells, which are defined as I just said. And we have differential equations that describe the change in charge in the two wells. And this one basically says the charge in the free well changes, it reduces as the consumption, so as the load draws off it, but it increases as the conductance takes place. Okay, and the change in the charge in the bound well is basically just affected by the conductance. So it just reduces as charge flows into the free well. And it's useful to introduce a variable k prime, which is k over c times 1 minus c. So you can think of k prime as being kind of normalized according to the widths of the two wells. And then we can define these two variables, which are the critical variables for describing the discharge processes of the battery. Delta, which is H2 minus H1, and gamma, which is Y1 plus Y2. Okay, so what we're doing at this point, we're simply assembling all the components of the model that we need in order to arrive at a collection of differential equations, which we will then build into our PDDL plus representation. So I'm going to kind of step through the process of arriving at the differential equations that we need to build into the model, because if you just look at the PDDL plus model without having seen that development, it's quite difficult to understand what the effects and the conditions in those PDDL plus actions mean, or why they're there. Okay, so given those variables and their definitions, some algebra and rearrangement leads to us defining y1 in terms of this expression, which can be simplified into this, and that allows us then to obtain the dead battery condition. The battery is considered dead when the charge in the free well, so the available charge, is less than or equal to 0. Okay, and in that case, since y1 is this expression, that means this expression is less than or equal to 0, which gives us that gamma is less than or equal to 1 minus c times delta, which is something that we can put into the precondition of an action and check. Okay, so just coming back to what Derek was talking about, less than or equal to here, again, this is the same subtle issue that we had before, that you really want to say when y1 equals 0, then your battery is there, but because of accuracies, we might not actually detect that exact instance where the battery is dead, so we say less than or equal. Okay, so now we have the dead battery condition, and of course, in this particular problem or application, we don't ever want our batteries to become dead, because what we want to do, or at least not until all the charge is gone, what we want to do is whenever a free well is looking like it's getting dangerously low, then we want to rest that battery so it can recover, and we switch to another battery. Okay, so now we've got a certain amount of the behaviour of the model set up, but we want to obtain the differential equations in terms of delta and gamma, which are our two key variables. So basically we kind of go through some algebra which is much condensed here, but I'm sure you see the point. So we want d delta by dt, which is given by dh2 by dt minus dh1 by dt because of the relationship up there. And then basically we just work through the process by algebra. This is the point at which we use the differential equations for y1 and y2, substitute them in and do all the algebra, and out comes this result that d delta by dt equals it over c minus k prime delta. Okay, so that gives us a differential equation for delta, and now we also want one for gamma, which is much simpler because d gamma by dt is dy1 by dt plus dy2 by dt. And if you look at those two things, then clearly the k's are going to cancel each other out, and you're just left with minus it. Okay? So now we have the two differential equations that we are interested in that capture all of the key behaviour of the battery that we care about. These two capture the discharge behaviour of the batteries and the recovery, and those are the differential equations that we presented in the paper without really going through the process about how they are arrived at. Because in some sense, when you look at them, you sort of see what's going on, because you can see that the height between the two wells is affected by the draw on the load and the conductance that's going on between the two wells, and that the difference in gamma is just kind of decreasing as the load takes the charge off. So there's kind of intuitive, but still, if you haven't got those to start with, and you're just given a model like the kinetic battery model, and you've got to render that as PBBL plus model, then you have this sort of work to do to get to that point. Okay, so we also know at this point that we have some initial conditions, which are that when t is 0, delta is 0, and also gamma is equal to the full capacity of the battery. And our equations, as I mentioned, tell us that the height is increased by consumption and slowed down by recovery, and the total charge is decreased by the load applied. Okay, so that's then our whole model. Okay, so I want to step lightly through the solution of these, because it's very useful for understanding the behaviour of VAL on the final plans that are generated. So if we look at our differential equations, we now want to solve them. This one's the easiest one, obviously, and the solution is gamma is minus IT plus A, and given our initial conditions, because gamma is equal to the full capacity of the battery at t equals 0, this is the solution to the equation, where big C is the capacity of the battery. For this other one, we need an integrating factor, and this is detailed, but it's necessary because this is how you see what's going on when you look at the BAL report. So the integrating factor is e to the integral of k prime dt, which is e to the k prime t. And now we are going to solve that, and basically we get to the point where we have this delta equal to these two components, so I over c k prime plus b over e to the k prime t. Remember, k prime is just k over c times 1 minus c, and if you work through all the algebra, you'll see where that happens and where k prime comes into it. And now we can use our initial conditions to get a value for b. So delta is 0 when t is 0, so therefore I over c k prime plus b is 0, which means that b is minus I over c k prime. Okay, so now we've got an initial state value for b, and plugging that in, we end up with delta equals I over c k prime times 1 minus e to the minus k prime t. So at last we have something that tells us that there's going to be negative exponential behaviour going on, and we obviously expect to see that in the VAL report when we look at the validation of our plans.
So Maria, you're assuming that I is constant, right, when you're doing this?
I is a load which is constant over a time period, but it's does whatever, alternates. I'll show you an example. Okay, so finally, these are our solutions then, and we will see the importance of those when we come to look at the validation of the plans. Right, so having looked at the details of the mathematical model, we're now going to look at how to render that in PBBL+. So PBBL+ is an extension of PBBL 2.2 for the modelling of mixed discrete continuous domains, and it consists of these components: continuous processes, controllable discrete actions, and uncontrollable discrete events, as Derek has just been presenting. And the details of the language are presented in this 2006 paper, where we give both the syntax and the motivation for this language, but also formal semantics in terms of hybrid automata. So there is a very close relationship between PBBL+ models and hybrid automata, as we will see. So looking at the PBBL+ model for the battery domain, it consists of a durative action to use a battery, which identifies the battery to be used and then chooses a duration for that use, so the planner chooses a duration for the use of that battery, and at the end of the period, having switched the battery on, the battery is then switched off. And when the battery comes on, that triggers the consumption of charge from the battery. And the effect of the process of consuming the charge is to decrease the charge in the available well according to the load, and also to increase the difference in heights of the two wells according to the differential equations that we've just been looking at. Well, as soon as the height difference between the two wells is non-zero, the recovery process begins, and that decreases the difference in height between the two wells according to the recovery process. Finally, we have an event when the battery goes dead, which is triggered as soon as the precondition, the dead battery condition, is satisfied. So that is when gamma is less than or equal to 1 minus C times delta. Now, the relationship between the PDVL plus model and the hybrid automaton is very strong, and hybrid automaton theory was developed in Hensle's paper here, the 1996 paper, and that, I'm now going to show that relationship, how that relationship works in detail. So this is a fragment of the hybrid automaton model for the battery domain, and it's showing the state transitions of a single battery. So in this picture we can see the control modes of the battery, and some of the switches between those control modes. And we note that within the control modes there is both logical state, so the battery can be either on or it can be off, and there is also the continuous state, which is given by the differential equations. So the flow conditions when the battery is on is determined by consumption and recovery, while the flow conditions when the battery is off is determined just by the recovery process. When the system transitions between states, the variables are updated, and there are also jump conditions, which in this case this is the condition, the battery dead condition, which force the system to leave the state that it's currently in. And we have this special variable, the time slip variable, which we maintain the invariant that time slip is zero whenever the system is in a state. As soon as the time slip becomes non-zero, the system must exit that state. And when the jump condition is satisfied, the time slip becomes non-zero. So here's the model for the overall controller, which demonstrates how that works. So this model describes the transition between two states, one where a load profile is being satisfied by the system, all's going well, and the other when the system exits that state, either because of a dead battery or because of non-optimal behaviour, and it enters a state in which satisfactory service, which must be maintained at all times, is no longer being maintained. So what we see in this first control mode is the conditions under which the time slip becomes non-zero. So these are the conditions triggering a non-zero time slip. The first one is where there's load but no battery to service it. So in that case the battery has died. And the other case where there's no load but a battery is on, and in that case we have a non-optimal assignment of the battery because it's not servicing any load. And in those two cases, T dot becomes 1, and then we're forced to exit the state that we were in the battery part of the model. So the complete hybrid automaton for the battery system is the cross product of this machine with the machines describing the behaviours of the individual batteries. So now we come to how do we define the initial state for a planning problem in the battery domain, and it's defined by specifying the parameters of the battery. So we have some number of batteries that we're going to be switching between, let's say 2 as in this case. And we specify the parameters of the two batteries because they might not be identical, and we also specify the load using timed initial literals. So our load is going to be a discretized curve which changes at those timed initial literals. And notice that in the initial state we provide the satisfactory service condition, and we also initialize the system with no load being serviced. And then the goal is to have finished the servicing of all of the load, which can only be done when the all done condition is achieved. And there's an additional action here which just captures that. The precondition is that we're all done and that satisfactory service is available, and the effect is that we're finished, and that's the end of the planning process. There is a subtlety in this, as can be seen here. So when we specify the load profile, what we do is we identify a time point which corresponds to the sum of the capacities of all of the batteries, and the area under the load curve will be equal to that sum of all of the capacities. And that basically says that we can only achieve a finished plan if we're able to consume all of the charge from all of the batteries. But in reality, we know that that isn't actually possible. We will actually only consume some quantity less than that maximum before the batteries become effectively dead. So what we try to do is to push that C prime, which is less than C, as close to C as possible by finding the longest possible plan. And the details of that are provided in the journal paper that I mentioned. So here's an example of such a plan. It basically switches between the two batteries available, and the key thing is that these are the times at which the switches take place, and these are the durations determined by the planner over which each battery is in use. And then looking at the VAL report, Derek showed you an example of a VAL report for the bouncing ball situation. Here we see that VAL is actually computing the analytic solutions to the differential equations that we produce, and it's doing that at each happening. So whereas we solved them for the initial conditions in the initial state, VAL solves them for the initial conditions at each of the time points and states that it encounters along the execution of the plan. So these are the points where it's solving the delta differential equation for the two batteries, and basically if the battery is loaded, then the I value is non-zero, so you get this term. If the battery is not loaded, then the I value is 0, so that term disappears. And of course in our solutions in the initial state, we had a value for B that was dependent on I, which would also be 0, but as we step through the plan, the value of B is not necessarily 0, so that's why you still see that term. So VAL is doing the work of solving those equations to ensure that the batteries are not, that the battery dead event is not get triggered. Okay, so what we have here is the graph of gamma using half-minute loads. So what you see is the sort of linear effect on gamma, which is, and then the curve is flat when the load is 0. So you get this kind of stepping function all the way down to the point where if we kill the battery by using up all the charge. And then this is the graph of delta, which is more interesting because this is the height difference increasing as charge is drawn off, and then decreasing as the battery recovers, and then increasing, decreasing, etc. And of course those are not straight lines, those are curves, so this is non-linear consumption and recovery effects that we saw in the differential equations. And then if we use much finer grained load intervals, then you can see in the graph of gamma, you can see the tendency to linear drain. You've just got a nice straight line. And with delta, you see this negative exponential tendency inverted because we had minus e to the minus kt. So that's quite nice. And the smaller grains the load load periods are, the smoother that behaviour becomes. So these graphs somehow correspond to the actual engineering data for the batteries, so we know we have modelled correctly the behaviour of the battery and captured it in the process. Okay, so that's a sort of worked example which I thought would be useful to see, because you can get tangled up in the philosophy about PDBR+, and you have to see how to actually use it in a particular situation where it's not obvious from the start. It's not obvious from the start whether a process event model is necessarily better than a derivative action model and so on. But I'm not interested in that. I'm interested in what can we capture with PDDL plus language, and can we sensibly write down something that corresponds well to the mathematical model that describes the behavior of the system that we're interested in, and then can we actually solve that. So we are now going to take a break for coffee, I believe, and then Dan will talk about solutions.